Can you guys hear me all right?
Yeah.
Great. While we're waiting for a few more people to log on here, I'd like you to write in the chat box something you know now that you didn't know before the class started. So tell me in the chat box something you know now that you didn't know before the class started. So you're writing in the chat something you know now that you didn't before the class started. I suppose if you're out jogging somewhere, you don't have to write in the chat. You can just think about it. See if I can find out what you have been writing. Only 4 people have written something, it seems. Or there's 4 unread, it says. Okay. David Smith, I'm going to put you on the spot. You said you learned something about the physics behind chip formation. Can you tell me something that you learned about the physics behind chip formation?
Sure. Sure. With physics, I learned more about how it expands, how the chip expands as you go further in the as the chip.
The fact that the chip is thicker than the uncut chip thickness?
Yeah.
Yeah. Okay. And that's because we put a lot of energy into the workpiece material when we form that chip, and it smushes stuff together. The technical term is smush, I think. All right. So Eli learned how to read a bore gauge. And we're going to talk. We talked about measurement and metrology last week. But next week, when we talk about the GD&T stuff, we're going to really start to understand why that measurement and that measurement uncertainty is important. So reading that bore gauge is actually really important. The meaning of technobabble. I didn't coin the phrase. I learned it from somebody else who claims to have learned it from somebody else. We talked about the concept of Six Sigma. And especially if you're gonna have a job in manufacturing, just understanding that Six Sigma or a job at a company that does manufacturing, whether your job is directly related or not, understanding that concept of Six Sigma and of doing quality control instead of quality inspection. So if you don't make any bad parts, you don't have to do inspection. So I like that. Let's see. How to use a spree. Eric, I think you're possibly overstating your abilities, but maybe not. I had a student, and he was working on a project in the machine shop, and he's working with the professor, and the professor had this idea that he could learn something about the machining operation if he set up a program to do some controlled cuts on the machine. So set up an experiment, and then they change one parameter, and then they note the results, and then they change that parameter again, they note the results. So it seems like a good experiment. He had a student who needed some, I think he was doing an independent study. He needed some credit. And so the professor asked me to teach the student how to operate the machine well enough so that he could load the workpiece in the vise and close the vise handle. You guys did that in the first day, in the first 5 minutes, right? So I had to teach him how to load the part in the vise, close the vise handle, close the door on the machine tool, press the start button, and observe what happened. So you guys all did that within the first half hour of your first lab, probably. And so I taught him that much, and then there was one parameter he would adjust. He would resend the code to the machine tool, and he would repeat that. And so he did this for several hours. I don't know, maybe he did it for 15 hours spread over like 3 weeks. And at the end of that, this student came to me and he says, Professor Bergstrom, I can't believe how much I didn't know about engineering before I learned how to operate the machine tools. And I thought, that's really cool, because you didn't really learn how to operate the machine tool. You learned how to stand in front of the machine tool and watch it do something. But I thought his attitude was really cool. And then that was like D term, beginning of D term, end of C term. In the summer, and that's what he did. That was his experience in the machine shop. And then in the summer, he asked to become a lab monitor, and our process at that time was a little bit less formal than it is now. We hadn't quite figured it out. But he asked to become a lab monitor, and he says, can you please make me a lab monitor? I know how to do CNC machining. I looked at him, I said, Wayne, I think you're overstating your ability here. You know something about CNC machining, but I wouldn't say you know how to do CNC machining. So thank you, Eric, for your optimism on knowing a spree. Sorry. But so Wayne, by the way, I ended up advising his MQP. He did a fabulous MQP later. And then, and today he owns a manufacturing company, has about 50 employees. So I think he did learn something about CNC machining. But I don't think he learned it all in that first 3 weeks. Physics behind chip formation, concepts of Six Sigma, how to use CAM, learn how to use a spree, learned about machine tools, about CAM. You know, it's interesting. All right, I'm going to quickly, in the next 30 seconds, write what's the most important thing you learned this term, and it doesn't have to be from this class. Usually when I ask people to write something they learned this term, somebody in the group includes something that wasn't from this class. But what's the most important thing that you've learned that you didn't know before a term started? Just quickly write it down there. There is a method here. Self-learning habits. How to take a COVID test. We've all learned that. I have one coming up in a couple hours. Come on, write them down. I'll shout them out. How to take a COVID test. Self-learning habits. How to practice reading sheet music. How to cook fried chicken. That's a good one. How to use a thermostables. How to use thermostables. How to make dinner. How to cook. I learned something new about cooking during the COVID crisis. I learned how to cook sous vide. That means under vacuum. You can take, so say you want to have a steak and you want to have that steak medium rare. So the temperature for medium rare steak is, I think, 123 degrees in the center. If you put it in a vacuum sealed bag and you put it in water that's 123 degrees and you let it sit there for an hour, the whole steak becomes 123 degrees all the way through. Then you take it out 1 minute on each side in a hot frying pan and you have a perfect steak. How to cook. How to juggle 4 classes. Ooh, somebody's overloading. How to take classes, the possible reason for 5-year requirements and jobs. How to manage to make sure I get stuff done, but also have time to make food and relax. So we've learned a lot about life this term. and especially especially with the special circumstances of A term. I mean, I think if you asked me this question in A term at this point, my freshman year, and about, I don't know, 40, 50% of you guys are first year students. I think, let's see, I lived in Stoddard. I lived in Stoddard C, the room right next to the main entrance door. I learned to be annoyed when people knocked on my window because they wanted to get let in the building. That was important. I learned how to convince upperclassmen to buy beer. That was important. Actually, it was really good to have one that lived down the hall in a single. Learned how not to get caught by the RA after the person bought you beer. I don't think I learned as many great life experiences at the beginning of my freshman year that you guys have learned. So maybe it was just me, or maybe you didn't want to write about beer in the chat. I don't know. Let's move on though. So when we ended yesterday, what were we talking about again? Somebody remind me. Say again.
Stress, strain, and fixture design.
That's what I said we're going to talk about today. That's not what we ended on yesterday, right? I guess we ended on yesterday me saying that's what we were going to talk about today. Just before I said that, what were we doing? Were we looking at orthogonal forces at the edge of the chip in that chip workpiece interface? So I think we had this diagram up. In fact, I know we did because I just erased it. Right, so this is our workpiece. This is our tool. Right, this is our chip. The chip's moving that way. The workpiece is moving that way. Or you could say the tool is moving this way. Is that correct? And so there were some force systems that we talked about that were important in understanding what's happening here in this deformation zone, the part where the chip is forming. There was some force system we talked about. What were those force systems? Can somebody remind me what the forces were?
One was F cut plus F thrust equals P.
So we've got this cutting force, this FC, and we have a thrust force, FT, and you add those together, and you get a resultant force that we'll call P. And so one of the other things we learned was that all of the force systems that are interesting to us in understanding chip formation, they add together to equal this resultant force P. So this force P here, that's the force that is making the chip form. What is the primary thing that gives us this FC? Where does FC get generated in the background?
And that's from our machine tool.
It's from our machine tool. Specifically, it's from the rotation of the spindle, right? So FC comes from spindle rotating. This velocity here is the surface speed. And we know that the power that goes to the spindle motor, P, C, equals FC times V. We know that because physics says so. The units say so, right? Engineering's math, just a bunch of word problems, cancel the units. So if the units work, this must be true. And power equals force times velocity. This thrust force, that comes from the servo motor that's controlling the axis. And so what's happening here is as the chip slides along the edge of the tool, that friction, it wants to pull the tool away in the direction that the chip is moving. To counter that, we've got to push down with something. And so we've got that thrust force that keeps the tool in place so it doesn't get pulled away by the chip grabbing onto it. And so we've got our FC and our FT, they add together to equal P. This is interesting because we can measure the power that goes to the spindle pretty easily, and we know what the velocity is because we told it what velocity to use. This FT is interesting. We can also measure that. We could measure it by measuring the power that goes to the servo that's doing the pushing. That's a little bit more complicated because there's more friction forces and there's more uncertainty depending on the angles of loading on the bearings and stuff like that. It's really easy to get. So remember, we also had our P equals, what was it? KP times W times Q times C. And if we have the power at the spindle motor, we need to have this E factor in here too, right? This efficiency of the machine tool. So KP equals these things, or sorry, PC equals these things, and it equals these things. If we're measuring the power at the spindle motor. And this E is pretty easy to understand when you have rotation. It's hard to understand when you have linear motion caused by rotation with dynamic loading in multiple directions. So we don't usually use power on the motors to understand this. What we'll do is we'll put a 3-axis force sensor either under the tool or under the workpiece, and we'll measure these forces directly often when we're doing these kind of experiments. Okay, but we can measure that stuff. That's cool. That's not what causes the chip to form though, right? The chip forms when we mush this material together here in this rake plane, the shear plane. That's where the chip forms. And so we've also got a force system that lines up with that. What do we call that force system? What are the forces there?
There's, I think it's F parallel to the shear plane and then F normal to the shear plane.
Yeah, we have the F shear, which is along the shear plane. And we have the normal to the shear plane one. And those again add together. So this one must end here, right? Easy thing about geometry. So there's that shear force that's causing that shearing to happen. And the way I've drawn the angles here, I guess it's not a very strong material because it didn't take a lot of shear force to make it cut. And so that's interesting because it's telling us what's happening to the material, right? It's directly related to this KP somehow. It helps us understand what's going on inside the material. If we change things about the material or we change things about the shear angle, we change the shear angle by changing the uncut chip thickness, or by changing the rake angle. Those things are cool. All right, so that helps us. And then of course there's the forces that line up with the friction plane. So we've got a friction force, and that's trying to pull the tool that way. It's the chip pushing on the tool, and then we've got normal to the friction force, right? And those add together and to equal P. And because these are all orthogonal force systems, I think it's the vector term is the dot product, right? We can use dot products to move from one orthogonal force system to another, right? And we can figure out the equations to move from one orthogonal force system to the other. And I could, I suppose, if this was a 14-week long class, maybe we'd spend the next 2 weeks having you derive all those equations the same way we derive the equation for converting from RPM to surface speed. But we don't want to do that. It's about that 5 years experience, right? Somebody wrote in the chat, they learned that it was important to have 5 years experience, and it's so that you can not only have the books, but know which book to look in. And somebody once told me that engineers don't have to know anything. They just have to know which book to look in. And so what we're going to do here is we've got a reference guide, and I updated the Canvas site quite a bit. Let me share a little bit. I don't want to overstate anything. It's like saying I know Esprit. I've updated the Canvas site. I made it clear this is how you run a spree in the web browser, this is how you install it. But also, if you go to this equations in ME1800, it's a list of what I think are all the equations we use throughout the class. So we had profit rate here. We talked about this RPM and SFM. Talk about RPM to feed rate. This is just a demonstration again to talk about the difference between radial depth and axial depth. So axial depth is how far the tool goes down into the workpiece. The radial depth is how far you step over. Remember, I said the three most important process variables in machining are feed speed, depth of cut, and width of cut. So the four most important variables are feed speed and depth of cut. So now this is when we talked about, remember that tool nose, as it gets dragged across the part when we're doing the turning operation, it makes a surface that looks like this. And we can actually, if we know the surface roughness, we can determine what was the tool nose radius and the feed rate. Or if we know the tool nose radius and the feed rate, we can estimate what the surface roughness will be. That's pretty helpful in designing the process if you need to have a particular surface roughness. Material removal rate is simply the volume of material over time. There's a bunch of different formulas that you can derive based on knowing that. We've got our power for chip formation. This is, you look these constants up in the the machinery's handbook. And I have confirmation from the library that we have unlimited access to this book. They used some kind of grant or something to make sure that they paid for this book because I said we needed it for ME1800. So you can get that on the library's website, the way I showed yesterday in class. And here's some example values for KPs. So for rolled aluminum, the KP is 0.33. For stainless steel, it's between 0.6 and 0.88, depending on which stainless steel it is. And again, we're using these numbers to do an estimate. So if you want the worst case estimate, you might want to use the 0.88 number if you don't know the details. And so our feed factor here, so our feed factors go from about 1.6 if you have a really low feed rate to about 0.8 if you have a pretty fast feed rate. So you can work that out, pick those numbers off the chart. Tool wear factors, again, it talks about the different types of cutting, the different types of things. You can look that up on the table. Now, this one I don't think we showed yet. So let me, yeah, I'm going to switch off the sharing. We're going to do this on the board for a second. I think it's a little bit easier to do if we think about it. And so part of the problem is just visualizing the directions and orientations of the tools and the chips relative to each other. And it's one of the reasons people have trouble grasping this. And I've got some other videos that I've done where it's really pretty well explained. And so I'll find some of those clips and I'll share them on the site also. But in our turning operation, we've got our workpiece that's turning here. We've got our tool that's over here. As the workpiece turns, the tool moves along the edge of the workpiece. And we've seen it happen. You've all run the lathe, you've made a part, you've seen those kind of turning operations happen. If we draw a diagram of it, we've got our workpiece, we've got some material that's been removed. With some material that's been removed. And so our workpiece, so if the workpiece is rotating in this direction, so it's spinning like this, then the tool would be down here. Again, engineer, not an artist. So the tool's down here. We're looking top down at the rake face of the tool. So that's the top of the tool insert. The chip forms and it slides along this rake face as it goes out. So the feed is in this direction. The rotation is in this direction. So the surface speed is straight in and out of the board in our diagram. And the surface speed, so it's interesting because we've got two diameters now, right? We've got an original diameter. We get a final diameter. So we've got two diameters. Our surface speed is the circumference times the RPM, either multiplied by 12 or divided by 12. Is that true? So the surface speed is in this direction. Which diameter should we use? The outside diameter or the inside diameter? Anyone want to guess? Anyone have a strong opinion which one we should use?
The inside diameter, because that's where the tool actually is.
So the tool tip is at the inside diameter. So if we're interested in what's happening here, then we definitely want to be using the inside diameter when we do that calculation. If we're interested in what's happening here, why might we be interested in what's happening out of the outside edge instead of the inside edge? Maybe there's something wrapped around the part. Too much force will make it fly off. That could be. It could be a coating on the part. Too much force could make it fly off. We might be caring about that. So we might be caring about the maximum surface speed that's happening. We might be caring about the minimum surface speed that's happening. If we're just trying to understand stuff about the cutting operation though, it's really often, I'll take the average, halfway between the outside diameter and the inside diameter. And that's giving me, because whenever we're doing these calculations, it's almost always because we're trying to estimate something, right? And so anywhere along this, the changes aren't going to be that different from each other. And so you can really use the inside, the outside, or the average. In quiz questions that I create, where you're supposed to calculate a surface speed for a turning operation like this, I always use the average, but then I have it accept answers that are the minimum or the maximum, just for doing that. All right, so as we do this, now, remember as we're dragging our tool along, there's a radius here. So we're actually making a surface like this on the part. Right, so this distance between these peaks and these valleys, that's the feed in inches per revolution. That's the feed. And so the chip thickness, so this distance, the thickness of the chip, has to do with that feed rate. How far did it move per revolution? But it also has to do with this side edge cutting angle. So if the side edge cutting angle was 0, if the tool was perfectly vertical and the chip was coming out, the uncut chip thickness, T1, equals the feed rate. Since in most of our operations it's not, it has an angle. We have a side edge cutting angle. The feed rate, the uncut chip thickness, is going to be equal to cosine of the side edge cutting angle, side edge cutting angle, times the feed. And so cosine of 0 is 1. So that works if the tool is perfectly straight, it equals the feed. If the tool is angled, this is T1, uncut chip thickness, equals cosine side edge cutting angle times feed. And you can figure that out with the geometry. And in my slide here, I sort of zoomed in on the chip. And we can see that if I go back to this screen share. Here. And so what I just drew on the board there, we're talking about this interaction right here. You've got your side edge cutting angle. On the slide, I call that side edge cutting angle beta. And so T1, that uncut chip thickness, equals feed cosine side edge cutting angle. When we know that, then we can come over here. We can take our chip, and we know the chip thickness because we picked the chip up off the bottom of the lathe and we measured the thickness. We can get our uncut chip thickness. From that, we can calculate the shear angle. If we know the shear angle, then we can calculate all kinds of different forces. So we can calculate the friction angle. That's the difference between the normal force and the resultant force here. F over N, so the force magnitude here divided by the force magnitude here equals tangent of that friction angle, which equals the coefficient of friction on that sliding interface. If we know this, we can go Ft times so you guys can read all the equations. Anyway, they're in here. And it's all based on this one relationship that we drew on the board yesterday. So we've got basically this circle here. You can translate the forces to any 2 points on the circle that are orthogonal. And the ones that are interesting are the ones lined up with the shear plane, the ones lined up with the rake face, and the ones lined up with the cutting velocity, the surface speed. Okay. So what is stress? I said today we're going to talk about stress, strain, and fixturing. So what is stress? Has anybody felt any stress in their life lately? Is the kind of stress that we feel in our life, is it the same thing as engineering stress?
No.
You don't think so? I think you're wrong. We'll see if I'm right or you're right. What is stress? What causes stress in your life? We've all felt stress lately. So what causes stress?
You mean mental stress or stress from an engineering?
Either one, I think they're the same.
Online learning.
What about online learning causes stress? I don't disagree. I just want to get to the root cause.
A change in the norm, perhaps?
Kind of.
Like how a weight on a bridge is going to be a change from what how it normally exists.
If we do online learning long enough, it will become the normal.
That's fair.
So it doesn't, and I would say that if we were sitting in the classroom right now having the same conversation, you would still be feeling stress right now in your life. Even if we didn't have, we have added stress from COVID and new experiences and new restrictions and all kinds of different rules, not even knowing what the rules are. And that's just the ones that are easy to think about, right? We also have conflict in the world. And I mean, so you guys are growing up. I guess technically you're adults, but you've grown up through this really amazing time period where technology changes faster than you could observe it changing, right? Nothing is the same next year as it was last year. At the same time, historically, we've caused all kinds of problems. We have all these race relation problems and protests, riots, police action, all these things going on, right? And it's all around you. So there's stress just from existing. For me, when I was a kid, it was the Cold War. I had Ronald Reagan saying that the commies were going to nuke us tomorrow. I grew up believing that the end of the world could happen this week. So we all have stress on us, and what that stress is it's pressure, right? It's things pushing on us, making us uncomfortable. And engineering stress is force over area. Force over area is pressure. It's the same units as pressure. So things pushing on it cause stress. Now, in engineering stress especially, but I think even in our mental stress, no matter what happens, if you apply pressure to something, it moves. So you can't apply pressure without causing some sort of motion or deformation. right? And there's an entire 7-week long course you could take in mechanical engineering here titled Stress and Strain. And so you could learn into all the minutiae of all this stuff. But the real important fact is every force applied over an area, so every pressure will cause some kind of a strain. And so strain is simply the result of stress. So we get strain in our mental life by, I don't know. I mean, sometimes it makes it so you can't, when the COVID shutdown happened, my oldest daughter did not come out of her bedroom for over a month. And she was already homeschooled. It's not like she got kicked out of her school. She already was homeschooled and she couldn't bring herself to leave her bedroom, right? Strain is what the effect of stress is. And so in engineering stress, it's kind of easy to do the math. We have our thing, it has a length, there's no stress on it, there's no strain on it. And then after we apply the stress, after we apply the pressure, the length changes. And so the strain is that change in length. And so it's a normalized change in length because we want to be able to talk about the strain on the marker or the strain on the eraser, and we want them both to be equivalent strain. So that's why we normalize it by the original length. If you do that, you can compare stress and strain for different items. And so I believe that there is a simple method to reduce stress and thus reduce strain. You guys ready? If you're dozing off, prop your eyelids open, find some toothpicks or something. All right. So stress could be reduced by simply changing the area. And a lot of us change the area by eating too much, right? Man, when I do this in the classroom, everybody laughs. Unmute yourself and laugh out loud, please. This is no fun for me.
Ho, ho, ho.
Ha 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 ha.
Put myself out there. I Photoshop
Yeah, I'm
myself.
smiling over here. There's some slack. You can't see it, but I am smiling.
I do hate that about the mask, because you can't see people smile.
Yeah.
Right. So what does it mean in machining, right? Oh, so if you relate the stress and the strain, you can come up with this elastic modulus. Elastic modulus is really cool because it tells you something about the bulk material properties. Right? Earlier in the class, we talked about things that we could measure, right? One of the things we could measure was hardness, right? But we can also measure elastic modulus. And this tells us a lot about what's happening. So each material and material conditions impact this too. So it's not just the material, but temperature and all kinds of stuff. But each material will have its own unique elastic modulus. And the elastic modulus of that material will tell us how much will it move. You can predict how much strain you will have for a given stress. Let's think about this in manufacturing. Somebody in a second remind me to turn off the screen share. And somebody tell me how much time we have left. Or
We have
We got
like,
like 11 minutes.
yeah.
I
depending
have a
on
question.
how much over I go.
I have a question, Professor.
Go ahead.
If you go back to that slide for just a second, on that formula for strain, it was like L1 minus L0 over L0, where L1 was the length after stress, like after the force was applied and there was stress, but that's also because it was longer. If L1 was shorter, that formula would still stay the same, correct? Say there was an inward force opposed to an outward force.
Yeah. If you do them in the one that you're subtracting from the other one should be the one that you normalize by. I mean, so in reality, on Earth, there is no object that doesn't have stress on it just sitting on the table, right? Because we have gravity. So there's always a force acting on the object. And so what you want to do is make sure the sign comes out the direction you want it to come out. So it's so yes.
What are you doing?
And if you want a more detailed explanation than that, you can sign up for the class stress and strain. But my rule of thumb is just make sure that the sign of the strain is the sign that I wanted it to be to do my calculation. So if I needed a positive number and I come up with a negative number, I know that I did the math backwards.
So if I wanted smaller than I naught, we should expect something negative then.
Yeah. Okay, what are we doing? We're doing understanding how this stress and strain impacts us as manufacturing engineers on the shop floor. So you guys have, let's see, in the milling machine, you've been working on your Y block, right? So far. And when you did that, you did all of the machining on the part of the workpiece that was not held inside the vise, right? You held the part inside the vise and you did machining up in space above the vise. Would you believe that sometimes when we do this machining, we'll have, so this is the cross section of my vise jaw, I got my parallel, I got my other parallel, my other vise jaw, and the other end of my vise. I might put my workpiece so that it's completely inside the vise, so that I have the maximum clamping force, right? I have the most ability to clamp it as possible. And that works for me as long as I don't plan to cut on the outside edges of the part, right? If all the operations I'm doing are on the center of the part, I can sink that part right down in the vise, get the maximum clamping force. If I do that, and I look at it from the top view, I've got my workpiece in the vise. And my vise going this way and this way. I've got a clamping force like this. Now, in all of these cutting operations, what keeps the workpiece from flying up out of the fixture? And some of you in lab had your workpiece come out of the fixture. What prevents the workpiece with the spiral on the flutes of the end mill, with the rotation of the end mill, it's trying to pull chips, put that spiral in there to pull the chips up out of the hole. But as it's cutting on the side of the tool on the thing, it's also trying to pull the workpiece up out of the fixture. So what keeps the cutting force from pulling the part up out of the fixture? And it is not gravity unless the part is really friggin' heavy.
Friction.
Don't think about gravity, it's friction. What's the friction force? What's the maximum friction force equal to?
The materials like the mu times the normal force.
There's like a normal force here. Both sides are equal because our vise is not accelerating across the table. Right? So those ends are equal. There's a friction coefficient between this and the maximum cutting force that I can withstand there is then N, that clamping force, times mu. As soon as my cutting force in the upward direction exceeds N times mu, the part flies up out of the vise. And in this case, probably breaks the tool. In the lab, I don't think we broke any tools because the parts moved sideways a little bit and we hit the e-stop because we noticed the parts moved sideways. But in this case, actually, I saw one of these where the part came up out of the fixture, stopped the face mill from rotating faster than the servo motor could stop, broke the connection between the spindle and the motor. I've seen that happen twice at WPI because the part came up out of the fixture. One time it was a belt drive machine and replacing the belt was $1,000. That's not a big deal. The other time it was a gearbox driven machine. Replacing the gearbox was about $12,000. Oopsie. You guys know if something breaks in the lab, we want you to send us an email. You send an email to ibrokethis@wpi.edu. all we want you to do is say what you were doing and what was the result. And if there's a cool picture of the broken stuff, please include the picture. So what were you doing? What was the results? What is the approximate cost to WPI for your mistake? Because if you were operating the machine, I don't care if somebody else set it up, if you were operating the machine and something breaks, it was your fault. So what's the approximate cost to WPI for your mistake? And what are you going to do next time to make sure it never happens again? And so you could break the $50 end mill, and we ask you to do that email. You could cause $12,000 damage to the machine tool, and we ask you to do that email. We don't ask you for the $12,000 or the $50. So that's one of the reasons we're able to get so many people to do machining here, is because we allow you to make mistakes. All right, so we're clamping on the part. How do you know mu? If you need to know mu, how do you know it?
Look it up.
Look it up. People have studied this, right? And it really depends on both materials. And so say the vice jaws are steel, the workpiece is aluminum. There's a mu for steel on aluminum. What if the vice jaws are steel and the workpiece is Teflon? In most instances, why do we use the material Teflon?
Low friction.
Because it has a low friction coefficient with almost everything that you might put it next to. So we love Teflon because it's low friction. And if we're building our mechanism that needs a low friction interface, we often have to machine Teflon parts. Now, if the mu goes down, how do we get more clamping force? So let's say we're machining Teflon. The mu is pretty low. You do know, by the way, mu can be higher than 1. Mu is not one of those things that only goes up to 1. You can have like a 1.6 mu. That's about the friction coefficient between the tires on your car and the asphalt pavement.
You could make kind of a jig to hold it, like have a steel block under it and maybe drill into it.
All we have is the vise, and we can't make a special fixture. What do we have to do if mu goes down? We have to increase the normal force, right? The only way to get enough clamping force is to increase the normal force. But we know from our study of stress and strain that no matter what the normal force is, there will be strain. And so if we want to machine a pocket in the center of our Teflon part, maybe we're making a bushing that a shaft is going to rotate in. If we want to make this round pocket and we make it this diameter here, and we go in there and we make the most precise cut that we can make. And we go and we rough it out, then we go, we do a finish pass. It's perfectly round. It's exactly the diameter we want. We take our shaft that's got to rotate in there and we test fit it before we take it out of the fixture just to make sure we didn't screw it up. What's going to happen as soon as we let go of the vise?
It's going to spring back and become an eclipse.
The pocket's gonna look like that, and it won't be round anymore. And your shaft will still fit in, because it didn't change this dimension that much. It will actually change a little bit because it squished like that. But your shaft will still fit in. But what's going to happen over time is because there's no support here and here, it's going to vibrate. And I think the technical term is it's going to waller out the hole. Now, I learned the term from one of my students who was from Tennessee, so I'm not sure I pronounced waller correct. But you've all wallered out the hole before. When you're drilling a hole to put a bolt through it, and then the bolt doesn't fit, and you take that drill and you go like this with the drill handle and you waller out the hole. You've all done that before. Anybody that was ever on a first team has done that for sure. You all waller out the holes. So what can we do to correct for this? Because that's really a problem. It's a thing. What could we do to correct for it?
Use 2 clamps, like one from each side.
Oh, yeah, we could clamp both directions. And if we get the same clamping force in both directions, and then we make the hole undersized, and we get everything just, and that could be, if you're setting up a production run to make thousands of these, that might be the solution, is to get a clamping jig. Now, if our outside part is round, it's a little bit easier because you clamp it in a collet that squeezes all the way around it.
Professor.
Yep.
Time.
Thank you. So you could do that. You could also, I suppose, know how much it's gonna elongate. And you could cut your initial shape to be an oval that when it elongates, it becomes round. Or like Doug wanted to do, you could build a fixture that holds it down instead of squishing it sideways so that you're not putting that extra force on it. And that's probably the best way to do it, is to not squish it that way before you cut it. In the business that I own, one of the things we do is we machine ceramics often. Now, I don't know if you've ever had a ceramic coffee mug and clamped it in a vise, but if you haven't, someday you should try that, because as soon as you get sufficient clamping force to hold your workpiece, the workpiece shatters. And so you can't clamp ceramics that way. And what we often do is we take a piece of steel and we take some super glue and we clean the ceramic face really good, and we clean the steel face really good with acetone, put the super glue on there, we squish them together, and then we clamp on the piece of steel. Or even better, we use a magnetic chuck and we just hold the piece of steel down with a magnet. So there are ways to get around this stress strain. Let's see, what are we going to do? So there's an equation here in the slides. I put the slides up on the page. Stress and cutting, yeah. And then we shear stress, yeah. I took that question out. There's a question I want to, if you have some time and you want to stick on here, I'll quickly go through the quiz questions.
Will you record that part?
Yeah, it's all going to be recorded. You know.
Okay, so long as you're willing to record the.
You got to jump off to go to another class. But I'll just quickly jump through
if you can record the going over the quiz questions, I'll figure it out later. Thank you. Perfect.
Thanks. Assignments. Week 3. Holy crap! It's week 3. I'm disappointed by week 3 this year. Week 3 is normally the week that people stop being excited about attending lecture. Happens every year, happens every term. And I get it. I wasn't excited about attending lecture week 3 either. Weeks 1 and 2, I was so excited I was going to be a great student. By week 3, I realized that I'm bored. I don't want to go to lecture anymore. And often I stopped going. I don't recommend that as a method. And so the first day of week 3, so on Tuesday, what you missed was I normally throw candy to the class in week 3. And if I ask a question and you answer the question, I throw you a piece of candy. I shouldn't say I throw you a piece of candy. I throw a piece of candy at the general direction where I think you're sitting. If we're lucky, I don't put anybody's eyes out. So I missed that. This has been a very disappointing week 3 for me, but I think the week 3 quiz will be okay. So go to week 3 quiz. Let's preview the quiz. And so again, these are all these questions where there's more than one version of the question. They all have the same words, different numbers. I have it set this week so that if you get the answer incorrect, it tells you what the correct answer was. That feature is not there so you can game the system and do the quiz 100 times, write down all the correct answers, and then go back through and just select the correct answers. That's not the purpose. Although I suppose if you need the 10 points that badly that you're willing to do that, I'm not going to stop you. The purpose for having it tell you what the quiz thinks the correct answer is so that you can check to see if your Excel spreadsheet did the calculation correctly. So if you build your Excel spreadsheet, please build the Excel spreadsheet before you do the quiz or as you're doing the quiz, right? If you build your Excel spreadsheet and it doesn't give you the answer that the quiz has, now you have a feedback, right? You have some data, and you can see, can I change my equation so that I get the answer that the quiz has, and then do the quiz again and do the calculation to get the right answer. If you do that and you determine that the quiz is wrong and you're correct, please let me know. But please also know that I can't fix it until after the quizzes are done. So just tell me about it and we'll fix it. And use the discussion forum to tell me about it so that everybody in the class can know that there's a problem with the question, not just you and me. All right, so you've got stock of a diameter of 0.75. Would you like to turn down to a final diameter of 0.7? You have a feed rate of 0.2. You have a spindle speed of 2,000 RPM. You need to figure out the material removal rate in inches cubed per minute. You guys can figure that out. If you don't know how to do it, you can look through the equation spreadsheet to find the equation that shows you that, or Google. You'll probably find an online calculator that does this for you. In fact, you could make an online calculator that does it. Milling operation, it's also axial depth, width of depth, radial depth, material removal rate. All right, so you guys can figure that out. Give me the following cutting operation. If the feed is this, material removal rate is this, the KP is this, the tool wear factor is this, what's the power at the edge of the cutting tool and horsepower? For this, you need the machinery's handbook. You got to look up whatever's missing from the equation. You'd like to drill a hole in steel of this hardness. The drill diameter is this. The drill press has a machinery efficiency of this. That's the E, right? Your spindle speed is this. A feed rate of this. You must determine the required power from the motor for the given operation. You will need to look up information from the machinery's handbook to find this question. It's going to be all in that same section that we were looking at in class. Got a facing operation on a lathe. You've chosen a rake angle of this. Remember, we choose the rake angle during the cut. You notice the uncut chip thickness is this, and the chip thickness is this. What's the resulting shear angle? Right, so we've seen that slide. It's in the equations thing. You're performing a milling operation. You know the measured power is this, thrust force of this, surface speed of this, angle of this. You must determine coefficient of friction. Again, it's in the equations. Material removal from a cutting tool. The cutting tool you have is selected, proceed friction force of 200, normal force of 160. What's the friction angle? I think that's F over N, right? You're operating a lathe at 250 millimeter diameter. All right. So this is one of the ones that I really wanted to talk about to make sure you understood the question. You're operating a lathe and the diameter of the manual chuck on the lathe is 250 millimeters. It started with a programmed spindle speed of 4,000 RPM. Now in class, we haven't seen a manual lathe. Oh, I wasn't sharing the screen, huh? Somebody could have told me to share the screen, but now I'm going to go back to the whiteboard anyway. But all those first questions, the answers in the equations slides. All right, we've got a lathe. We're looking at it. So this is the face of the lathe. There's some jaws here. There's a chuck key that goes in here. It's just a T-handle thing with a socket on the end that interfaces with the lathe. As we turn that chuck key, the jaws go in and out to clamp on our workpiece. So there's a manual chuck on a lathe. We say that this diameter here is 250 millimeters in my problem. We start the spindle at 4,000 RPM. Assume that the lathe has gotten to full speed before the chuck key flies out. We spin the lathe around. The chuck key is not attached, but we forgot to remove it. After, say, one revolution, there's enough friction because of the angular acceleration that it gets held in there. It makes one revolution. And then it stopped accelerating. There's no more angular friction here. And it shoots out in that direction, right? It's just like if you've ever done a sling where you hold it and then you let go on one side and the rock flies out that way and David kills Goliath. Right? The question is, and we give you the mass of the chuck key, I think here. Yeah, we give you the mass of the chuck key. The question is, how much kinetic energy is in the chuck key when it strikes you in the forehead? So you got to know the mass and the velocity, right? And then you can know the kinetic energy. So how much kinetic energy is in the chuck key when it strikes you in the forehead? All right, the next question. For a given turning operation, again, we got a turning operation. So just like the chuck key here, when I spin my lathe around, the jaws are being held in by, in the case of the next question, by a hydraulic pressure pushing them together. So we've got a hydraulic force pushing the chuck jaws together. The workpiece is in here in the middle. And we're clamping on that workpiece with hydraulic pressure, pushing the chuck jaws together. When I spin the lathe around, all the jaws want to accelerate in this direction, right? They have an acceleration in that direction. The force that comes from that acceleration reduces the effective clamping force on my part. So I've got a clamping force before I start because I know what the hydraulic pressure is. When I spin it around, we get that centripetal acceleration. The apparent clamping force goes down because of the mass and the acceleration of those chuck jaws. F equals ma, right? If you assume that all of the cutting force in the operation is trying to move the workpiece in the fixture, the maximum allowable cutting force can be determined by knowing the force due to the centripetal acceleration and subtracting that from the hydraulic clamping force. This is a real thing. It affects cutting parts every day in the lab. All right, so that's question number 9. Question number 10 is just please upload your Excel spreadsheet that you use to make all the calculations. So I believe all of the numerical questions in the quiz have the correct answers and grade correctly. With that said, I don't know that it's true. I just believe that it's true. So if you're struggling with a question because you think you're doing the math right and the quiz keeps telling you you're wrong, please post that in the discussion forum, post the question number and why you think you're right and it's wrong. That'll be pretty obvious. And I will investigate the question and I'll respond whether or not I think that you're right or the automatic grading is correct, but I cannot update the quiz once you have started it. So I can only give you full credit for getting it right, even though the question graded incorrectly. I cannot fix the quiz once a student has taken it. It's a thing in Canvas. In the old system we used, I could fix the quiz and then you could get it correct, but not in Canvas. So I thank you very much. Sorry for going over today. This is
question.
Yeah, go ahead.
With the equation sheet on Excel, we just use the equation stuff you send out to make that Excel spreadsheet?
Or any equation that you look up on the internet. I don't care if you use mine or somebody else's.
Okay.
And sometimes I'm willing to believe that other people explain it better than I do. I often look at other people's YouTube videos to make sure that I'm explaining it in a way that's easy for you guys to understand. What else? Yeah. Oh, so some advice on the Excel spreadsheets, because I haven't gotten feedback back to everybody yet. But I recommend, if you have an equation that you're using for something, to take a screenshot of the equation. So take a screenshot of the PowerPoint slide or whatever, and copy that right into the Excel page that you're doing the calculation on. So when you come back to it later, you can remember what that one is really about. So if you have a picture of the diagram in the equation, it makes it easier to reuse the Excel spreadsheet in the future. And I'm pretty sure I can guarantee that we're going to want to reuse our Excel spreadsheet when we do the final exam. In fact, if everybody does a good enough job on their Excel spreadsheet, they will all get 100 on the final exam, probably. That's never happened before, but I have faith in you guys. Could happen. Don't think they'll fire me if everybody gets 100 on the final exam. But then again, I don't know. They never told me I had to find out who's best. I just have to find out who's qualified to move on. Any more questions? Because I like to listen to myself talk, so I can keep talking for hours. All right, I'll see you guys later.
Thank you.
so much.
Thanks.
Thanks.
Thank you.
Bye.